Hello, we are on Module 2, Topic 3, Lesson 4, and we're only working on Activity 2. So it's been a while since we worked on these, but we're going to kind of re-familiarize ourselves with the varying methods that we have to solve a system. So with page 354, we have some systems here, and you get to choose which method you'd like to solve. We can either use the graph and use the graphing method to try to find the solution to the system, or we can try to use substitution. So it's one of the two. Now it's down to you to figure out which one is best to use. We're going to start with number 1. We're going to do number 2, but I made 2 different problems here, and then we'll do number 3. So for number 1, typically my best method is to, or my preferred method is to graph it in slope-intercept form, right? That means the equation has to be of the form y equal to mx plus b. It looks like these two are in slope-intercept form, so I would probably graph this, but with this, you may notice that the first equation, y equal to 5x plus 12, that would actually go off the graph. I think the highest we can go is 10 units. So it looks like we could try to do it, but that's probably not preferred. So what we're going to do is we're going to use the substitution method. That's where we have 2 equations that are solved for, and we're going to substitute them into one equation. So you could think of this as I'm taking the y of the first equation, I'm taking 5x plus 12 and substituting that into the y of the second equation. So it looks like this. So 5x plus 12 equal to 9x minus 4. So this is nothing new, right? We've done this before. But typically when I give you a system, I would typically say, right, solve using this method, right? It's down to you to choose. But let's go and solve this. So I'm going to, let's say I move variables to the right side. I'm going to subtract 5x to both sides. We'll get 12 equal to 9x minus 5x is 4x. And then we have minus 4. We'll move the constants to the left. So I'm going to have to add 4 to both sides. We'll get 16 equal to 4x. And if you divide both sides by 4, right, 16 divided by 4 is 4. And we're going to have 4 equal to x, right? Now, some students think that we're done with this equation. And if you're solving a multi-step equation, you would be. But since we do have a system that has a variable of x and a variable of y, you also have to find what the y value is. So you could choose any one of these 2 equations. Right, which one would you choose? I might choose the first one because they're both positive, or I might choose the second one because they're smaller, but I do see that we have a negative. For the purpose of this, let's choose the second equation. So y equal to 9x minus 4. So instead of x, I want to plug in a 4 in for x because we have 4 equal to x. So this will be, instead of 9x, 9 times 4, and then we have this other minus 4. Okay, so y equal to 9 times 4 is 36, and 36 minus 4, not too bad, is 32. Right, so this would be y, or for x comma y, this would be 4 comma 32. Now that, if I were to graph that, it actually wouldn't be possible on this graph because 432 is 1, 2, 3, 4 to the right, and then 32 up. So there's no way I'm doing that. Right, this kind of makes it a little bit better. Because I don't have to worry about the boundaries of a graph. Anyways, let's move on to the next one. So example 2, I got rid of, I didn't like the example, but I wanted a space to do this type of problem. So go ahead and write these 2 equations. So the first one is y equal to 1/2 x minus 5. And the second one is y plus 3 over 2x plus 9, or equal to 9. So the first equation is in slope-intercept form. The second one isn't, but I can get this in slope-intercept form, right? It's not too bad. With this, we typically need y equal to, and then our x variable and our constant. So how we do that, right? In order to move anything, we know to subtract. I'm going to subtract 3/2 x to both sides. Right, that's going to cancel it on this side. And we'll have y equal to, in slope-intercept form, we typically put our variable term first, our x term, so it's going to be negative 3/2 x plus 9, since it's positive. And this, right, so this is in slope-intercept form. We can identify the slope, we can identify the y-intercept. I'm going to write it one more time. Right, this is where, right, our m value is our slope, our b value is the y-intercept. So let's look at this one. We always begin with our, I'm going to change this example a little bit. I'm going to make this a positive 5. So I'm going to begin on the y-axis, always the y-axis here. So positive 5, 1, 2, 3, 4, 5 right here. And then now I'm going to graph based on my slope. So slope is rise over run, 1 over 2. This means I go up 1, right 2. So up 1, right 2. And we'll just continue that pattern. Also in the opposite direction, right? Want an accurate graph because we're finding where two lines intersect. We got to be super thorough and accurate with this, otherwise we could get a different solution. All right, and then the second one, our y-intercept is positive 9, so I'm going to go up 9. 1, 2, 3, 4. Oops, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, and our slope is slightly different. It's negative 3/2. Typically we have a negative, right? If you remember, we put it with one of the numbers. I'm going to put it with the numerator. Negative 3, that means I go down 3. Positive 2 means I go right 2 for my rise over run. So I'm going to go down 3, right 2. Down 3, right 2. It's this point also coincidentally. But let's continue the pattern here. Down 3, right 2. And looks like that's just about it. Let's go and connect these two, or these points. And we can clearly see here where they intersect. It is that point that I kind of bolded here. That is the coordinate, where it's always x comma y, the x-axis comma the y-axis. That is 6. Oops, nope. We went 2 to the right, so 2 comma 6. So this is the one value for x and y that makes both equations in the system true. All right, if you were to plug in, right, 2 here, right, half of 2 is 1, and 1 plus 5 would equal that 6 for the y. And you can also plug into the other one, but just wanted to show that. All right, and we're going to go through the third example, so to finish up this page, and then we'll talk about the assignment later. So here, neither equation is in slope-intercept form, and I wouldn't say that any equation is like easy to get in slope-intercept form. So typically it's either substitution or graphing. So I'm going to use substitution. Now, in order to use substitution, one of the variables needs to be solved for, meaning the variable's equal to a constant and another variable. It's equal to another expression. I see that this first equation, though, if I can get rid of that 4, then I can have this equation solved for y. So let me just write this off to the side. It's multiplied by 4, so let me divide everything by 4. If I divide the first term, 4y, by 4, right, 4y divided by 4 is just y. If I divide the second term, 11, by 4, it's not going to look pretty, but it's going to be 11/4. And the last term, negative 3x, divide that by 4. This will be negative 3/4, and I'll put the x right next to it. Okay, so this means I can now substitute this. I can substitute this expression in for y of the other equation. So right here. So let's write what that looks like. It's gonna be a lot of writing. So I think it's important to give like varied examples. So this is like a little bit of a higher example. So we're gonna have 3x plus 2, and instead of y, we'll have 11/4 minus 3/4 x. And this is all equal to negative 5. Now for this, we do have to simplify. We only have x, which is what we want. but I have to distribute here. I have to multiply everything by 2. So you can think of this as, right, I'll rewrite the first term, 3x. 2 times 11 fourths would be, right, I'll put it up here. It would be 2 times 11 divided by 4. I could put this over 1, I could put this as 22 over 4, but this can be simplified. I could divide both of them by 2, and 11, we would get 11 halves. So what happens here, when you multiply by something, you actually just divide the numerator or denominator. So how this becomes 11 halves, cut this, right, divide that by 2, cut this, divided by 2. So the term that we get, instead of 11 fourths, we'll get 11 halves. Minus 3 halves x. And this is all equal to negative 5. Now, we talked about how you can do anything to an equation as long as you do to both sides. I see that we have a fraction with a common denominator here. You can either try to make everything a common denominator, but I prefer to get rid of those denominators. So this is something that we don't typically practice, but we have done this in a lesson before. Since we have a denominator of 2, what we can do is we can just multiply everything. We can double everything to get rid of that fraction. So I know a lot of students don't like fractions, so this is the way to get rid of it. So let's multiply 2 times the first term. Right, that would be 2 times 3x, which is 6x. 2 times this second term. So 2 times 11 halves, you actually just cross off the denominator because 2 divided by 2 is 1, and we're left with just the numerator, so just with 11. Same thing happens here. We're left with just a negative 3, and I'll keep the x. And on the right side, negative 5, 2 times that is negative 10. And this is a better example. I'd rather deal with this than the 11 halves and the 3 halves. Okay. Anyways, from here, let's combine like terms. 3x minus 5x, or sorry, 6x minus 3x is 3x. 6 minus 3 is 3. And let's rewrite the 11 and also the negative 10. Let's solve for this. This is a two-step equation. So I'm not going to show this step, but you would subtract 11 to both sides. If you subtract 11 to both sides, negative 10 minus 11 is negative 21. At this step, you would divide both sides by 3. I won't write that, but we'll do that mentally. Negative 21 divided by 3 is negative 7. Okay. So this, yes, it's a lot of work, but this is really assessing our ability to persevere in problem solving, the ability to critically think, the ability to use varying tools at our disposal. But what we can do here is now we're going to substitute this and find what the value of y is. I'm going to use this equation here. So let's bring that here. So we'll have 4y equal to 11, but instead of minus 3x, it's going to be minus 3, and we'll plug in a negative 7 in parentheses. Okay. So let's go into keep. We'll have 4y equal to 11. Negative 3 times a negative 7 is a positive 21. We'll still keep the 4y. And let's add them, right? 11 plus 21 is 32. And at this step, if you divide both sides by 4, I won't write that, but 32 divided by 4 is 8. There we go. We have a value for x, a value for y. Our final answer is negative 7, comma, positive 8. Right, this will probably be like the most work you ever do for a problem, but I think what we did is we critically thought of what we need. We decided a method that we had to choose between the methods that are provided to us, and we found a solution for x and y. So if you plug negative 7 for x, 8 for y into any of these equations, it'll satisfy both equations. Okay. Now, for this next one, we're not going to do number 4. We're not going to do number 6. Number 5, we're going to say number 5 is a you-do. So I'd like for you to try to figure out, would you rather use substitution, the substitution method, or we have a graph here. Would you rather use the graphing method? Or you're welcome to also use both methods. Or maybe use the substitution method to get the answer, and then the graphing method to verify that answer. Is that answer correct? Okay. All right. We're just going to do this real quickly here. On the next page, 356, on Talk the Talk, it says, how do you choose? Right? How do you know which method to use? Right? Let's put graphing here and substitution here. Okay, for graphing, it's nice to use this when both equations are in slope-intercept form. So if you see that they're in slope-intercept form, you're probably going to use graphing. The thing is, the first example we had, they were both in slope-intercept form, but we did not use graphing. So we could use the substitution method if, let's say, right, the equations would be off the graph. Equations are off the graph, right? The numbers are too big, the solution is too big, and it would just be, right, it would take days for us to make like a lot of points for the points that are on the line of the graph. Okay, now for graphing, we did use graphing when they weren't in slope-intercept form, but they can be easily written in slope-intercept form. So we're just going to say it can be, we'll say converted to, instead of writing that, I'm going to put y equal to ... Where I can easily solve for y. The substitution method, this is best to use when one or both equations can be solved for. Right, where we have x equal to, or we have y equal to, and I can find the value for x and y and substitute that into the other equation. So, right, that's why we can use this when they're both in slope-intercept form. But anyways, that's all we're going to do for this. All right, let's go to the assignment. The assignment is on page 357, and we're not doing too many. We're just doing number 1. So the A, B, C, and D part. The backside, we're going to give that a little bit of a rest here. Just number 1. Okay. Anyways, let me know if you have questions. Let's get started on the assignment.